How's it going? Intertubers that are surfing. My name is Jameis, and I'm going to try to teach you a little bit about OCaml today. It's going to be an exciting time. So, I'm going to go over the history a little bit initially and kind of where it comes from and why we have OCaml, etc. But if you want to install it while I am doing that little intro, this is what you do. Hopefully you have a Mac. If not, there might be some other ways, like using Aptitude on Linux. I have no idea what you would do if you have Windows. You probably have bigger problems if you're running Windows. So yeah, and UTOP, so OCaml will install the compilers for OCaml and the bytecode interpreter and so on and so forth. And OPAM is a package manager for OCaml, and you will use OPAM to install UTOP, which is a wonderful REPL that is far superior to the default OCaml REPL. So I would definitely suggest downloading those. Hopefully you guys got all those commands written down somewhere, because I'm going to keep going. Okay. So OCaml is a functional language, but the O means objective, meaning that it's object-oriented, and it is a functional language while still having imperative paradigms included. It would like you to be functional, and I think it strongly pushes you towards a functional language, but if you want to do something like implementing a doubly linked list, which is pretty hard with a purely functional language, or relatively difficult, you can use their imperative methods for implementing difficult data structures. OCaml stands for Objective Categorical Abstract Machine Language, and apparently abstract machine is no longer part of the language. I don't even know what that part means. It's a derivative of ML, which then became Caml, and then Caml Lite, and then Objective Caml, or OCaml, in 1996 by a bunch of French dudes whose names I'm not even going to try to pronounce. It's still run by INRIA, and the French are kind of controlling the language, so yeah, there you go. Which is kind of interesting. You don't get many French programming languages. They're always from like Denmark or something. So the highlights of the language is it is a static typed language, which will make runtime type mismatches impossible unless you're doing I/O and so on and so forth. But it's really convenient, whereas a dynamically typed language like Python or JavaScript, you're constantly running into these typing errors during runtime. Typing errors are pretty much impossible with something like OCaml and Haskell, which is really, really nice for the programmer. But if you're programming in shitty languages like C++ or Java, it's just horrendously ugly, and the syntax is like rough, and you always have to do type declarations. But OCaml has type inference, which gives you the same feel of a dynamically typed language. It's really easy to read. It's terse, really compact. Not quite as terse as Haskell, but very terse, very powerful, really flexible syntax and grammar. It's pretty fun language. Haskell's, in my opinion, a little more beautiful, but OCaml provides the imperative functionality that Haskell has chosen not to provide, and that's, I believe, why a lot of industry, it's starting to be popular in industry. Actually, probably not as much as Haskell, but you get the point. Parametric polymorphism aids in writing really expressive functions, similar to something like generics in C++. And then exhaustive pattern matching. It'll warn you, if you're not familiar with functional programming, I'm going to show you what pattern matching is, and it will warn you if you have not exhausted all of your options, kind of like saying you need to cover every case so that you don't shoot yourself in the foot. And it's got a ton of compilers, bytecode interpreter, It can compile a bunch of different platforms. So they provide a lot of tools with OCaml. It's pretty wonderful. So we're going to do some example code. I want to thank Professor Stephen Edwards of Columbia because I kind of yanked this from his slide. He teaches the programming languages and translators course that I'm enrolled in right now. And he uses OCaml because OCaml is awesome. And Edwards is awesome. Therefore, you get the point. So this is, right here is a typical function declaration. Functions are first-class citizens, so you would basically declare a variable in the same way. This rec, just ignore it. It just means that map is a recursive function. If it was not a recursive function, we could just remove it. So let map is the name of the function that we are creating, and f is a function that we are passing in. It's a parameter. Now imagine that there's another parameter right here that's missing that we're passing in, and it basically gets matched on these cases. So these vertical bars are for pattern matching, and what we're going to be doing is we're going to be passing map. We're going to be passing map both a function and a list. And it's going to apply that function to every element in the list. So we're going to be pattern matching on a list. And this first pattern is kind of like the short circuit case for recursion. It's basically saying you're done. You're not going to make any more recursive calls. And if you're familiar with functional programming, the end of a list is the empty list, essentially. So this is saying once we've mapped over every element in the list, the next element we pass into map will be the empty list, and we will just return the empty list. So this is the short circuit, which will become more clear as I explain the next case. The next case is basically doing a pattern match on the list with the head of the list and the remaining elements of the list, known as the tail. And this is the cons operator. Basically, it's concatenating, it's prepending to a list. Like I could do one and then a list, and that would prepend one to the list. But this is how you pattern match, and it will store the head of the list and the tail end of the list in these variables. And then I can say locally I can scope the variable r and say let r be the function applied to the head element in r prepended to the recursive call. So at one element at a time, we're going to apply f to one element at a time, and we're going to recursively call map while appending it to the list. And you can start to get the feel of how terse this language really can be. You know, we're doing the short circuit in one line, or the base case, same difference. We're doing pattern matching, setting the variables, and taking care of a certain case, local scoping, and we're doing a recursive call and appending to a list all in one go. It's extremely terse. If you try to implement this in something like Python, it'll probably be 10, 15 lines. This is also clarifying what is happening here. List.map is OCaml's implementation of map. And if I just call it in the REPL, this is shorthand for just putting in the REPL, it will output the type of map. So map takes a function whose type is A, which means it can be any type, and whose output type is B. So this means take a function that takes in one parameter and outputs another parameter of different types. They could be the same, they could be different. And also take in a list as the next argument, and then you will eventually output a list of type B. So list of type A, list of type B, and this is the function you're going to apply to every element in the list. And then last of all, this little apostrophe means that once something has been applied to the function, that function now has a specific type. So I'll explain that in just a moment. But if I do list.map and I define a anonymous function right here, this is the syntax for defining an anonymous function. This states take in the element, take in one parameter, and then add 3 to it. And then this is the syntax for a list. So And if you're not familiar with functional languages, you'll notice that there are no parentheses surrounding the inputs to this function list.map. That's just how it is in a lot of functional languages. But basically, I'm passing, this is the first parameter to list.map, and this list is the second parameter to list.map. And the output is 4, 8, 12. It's added 3 to every element. Now we can do something called currying of functions. And so I'm going to use a function, and I'm going to partially apply the anonymous function to list.map just to the first parameter. And the second parameter is still not going to be applied yet. So we're currying a function. We're applying one of the parameters, and the other parameter hasn't been applied yet. And it will return a function that we can now use in the future. So I create a function called add5. Oh, I have an error. This is supposed to be 5. I'll change that later. But basically, I wanted to create a function that will add 5 to a list. So I've curried the function list.map with an anonymous function. And then later I can use add.5 and I can apply it to any list I want. And it will add 5, or in this case 3. Right, moving forward. I think I got everything. Okay. So this is kind of, OCaml is used a lot for compilers because it's really powerful with typing, just like most functional languages like to be, and statically typed languages, and so on and so forth. And this is kind of the basic syntax for defining types. And you can imagine defining a type in something like C, and how many more lines you would have to have, or something like Java, like an object-oriented language, how many more lines you would have to have just to do what is done here in one line. But I created a type called op. Let's call that an operator. And an operator can have type add, sub, subtract, multiply, or divide. So, right, pretty self-explanatory. And these are just, they're not strings, they're just a type. And then an expression can be either a literal, which is of type integer. So int is inside of OCaml. Literal is something we're defining as a name. And these are all names we're defining. But lit has a specific type of integer. Or it could be a binary operation and this is a tuple. This is how you define a tuple. And it can be a binary operation of an expression, an operator, and an expression. Now you notice that this type is self-referential. So while I'm defining the type expression, I am simultaneously using it in the definition. It's pretty fucking awesome, if you ask me. And it's just so terse, it's wonderful. And just as an example, I say let one equal the literal. So this is the constructor essentially for the type. I believe that's the right term, constructor. So I create one, and forever an operator is bound to, an expression is bound to this variable 1. And then I can say 2, literal 2. And then we know that the constructor for the other constructor for an expression is using binary operator. So now I can use 1 because it's an expression, and I can use 2 because it's an expression, and I use the constructor add for the op type, and I can create a new expression of named 3. So you can kind of, this is really, really small example, but you can kind of see the power of typing in OCaml. It's pretty wonderful. So here's a simple example of memoization. Actually not too simple, but it's just a cool example. I grabbed it from the really, really wonderful book, Real World OCaml by O'Reilly. It's free online. It's pretty similar to something like Real World Haskell. But we're going to create this, this Memoize function. I guess it's a function. And basically it's going to take any function and it's going to make it memoizable. So if you're not familiar with memoization, basically the first time you put in parameters, you'll calculate a result, and that might take a long time. But the second time you put in those same parameters, it's going to be constant time to access that, that return type. or that return value, because it has stored it in a hash table. And this is just, it's sort of like a Python decorator in that you can take any general function, pass it to Memoize, and now that function will be memoizable, or it memoizes. I don't even know how to conjugate Memoize, but you get the point. So we create a new hash table, and essentially we use this optional type called sum or none, which is probably just what the hash table find function returns, is sum or none, meaning null, or you have some bucket with value in it, like 1 or a string. And you just run a match and check first if it's in there, in the hash table. If it is, just return the value. Otherwise, run the function on X. And then once you've run the function on X, you will add it to your hash table. See? And this is just a named parameter, the tilde. You can also do optional parameters. Very cool. And then we just define a slow Fibonacci, recursive Fibonacci function for calculating the nth Fibonacci, or the ith Fibonacci in the Fibonacci sequence. Right? One-liner, bam. May not be efficient, but it's pretty cool. You can do that just right there, one line. So in our REPL, just to show you the Memoize type, it takes a function, just like before, and then it just takes a parameter, a single parameter of type int or type string, and it'll output a parameter of int or type string, and that type will be decided upon the first application because of this little apostrophe, remember. But this is wonderful because this is polymorphic, really simple polymorphic, parametric polymorphism. It's really, really simple as opposed to something junky like C++ or Java. It's just a nightmare. Then we see the type fib, which is int, right, which matches this type signature.
Your screen cut out.
Good?
I'm already plugged in.
I'm over the.
Yeah.
Sorry, folks. Give us 1 second. How about now?
Nothing.
Can you go to the desktop? Okay.
Any luck?
No. Why did it cut out? Try your laptop. Make sure it's not. Look at yours, either.
Okay.
When you go up a card, it says
You want to put on the pause music?
technical difficulties.
Sorry.
Please hold.
Great.
Sweet.
And one
Okay, you are.
You're good.
Wait like 30 seconds. We're going to
No, you're good.
Okay.
Wait,
There
Good?
yeah.
Okay, cool. Technical difficulties, no problem. Okay, so we got this wonderful polymorphic Memoize function that will memoize other functions. And this is showing the type signature of Fibonacci. It takes an int, returns an int. And so you'll see here, we're just going to rebind the term fib to be Memoize fib. And you see it still returns the exact same type signature. And it has decided to no longer be polymorphic, and has decided to be take an int and return an int. And you will time the lookup for 40. Bam, it takes 5 seconds, pretty slow, inefficient. It's a pretty big Fibonacci number. And then we run it again, fib 40, and it's pretty much instantaneous, the lookup. It's pretty fun. Good example of wrapping functions. Here I've got one more code example, a little more complex pattern matching. So this is code for removing sequential items that are sequential that are the same value. Really messing that up. Items in a list, if they're neighbors, they're adjacent and they are the same value, it'll remove them and just turn it into one value. So you can see this is super, super compact, and this is saying, it's basically going to take in a list, and it's going to pattern match on, this first case is saying, pattern match on either the empty list, which is the last value while you're iterating through the list. Again, this is the base case. Or match on the second to last value, because since we're looking ahead one value, we don't want to look past the end of the list. And we're just going to rename this match as list. Just, you know, a nice little syntax they have. And then just return, in this case, just return what you just matched on. It's pretty much the identity for two separate cases. Otherwise, match the head, and then this whole thing is matching on the tail, and we do a sub pattern match within that, where we match the second element of the list, or the head of the tail, and then we match on the remaining part of the tail, which we don't need, that's why we use underscore. And then we rename this entire thing. We could just name it tail, or we could name it X's, or whatever, right? I can't type for some reason. Dang it, well, that's too bad. That's supposed to be X's. And then you just say if X is equal to X2, if the head is equal to the next element, then don't include the first head element and just keep going with unique. Keep recursively calling unique with the tail, the entire tail. Otherwise, do append the element because it's not the same as its neighbor, and continue with the recursive call on the tail. I mean, this is so unbelievably terse. 4 lines. It's so ridiculously terse. It's just wonderful. I love it. And you can see the type signature again. Show you an example. We're calling unique on this long list, and it just removes all of the values who are the same value next to each other. And we could. This is also polymorphic, so we could use this unique function on a list of strings right here. Pretty clean, pretty sweet. That's it for the code examples, but just want to talk about the ecosystem really quick. They've got tons and tons of tools. You can run OCaml dep on a project and it'll generate a make portion of your make file for dependencies. It's really slick. And then OCaml opt, native code compiler for tons of different native environments. There's a bytecode compiler. I've never used OCaml debug, but they've, because the compiler is so robust, I can see all the errors anyway. But it's supposed to be really nice. OPAM, the package manager, utop, we already talked about that. You got to use utop, don't use the built-in OCaml REPL. Core is a library that re-implements OCaml's standard library. It's what they use in real-world OCaml, and it's used, I'm sure, all over the place. I haven't used it that much. We didn't use it in our class. We just used the built-ins rather than core. Merlin is a code completion tool for Vim and Emacs, and you can plug it in with Syntastic if you are a Vim user. And OCaml Lex and OCaml Yak. These are tools for building grammars, for building parsers and building scanners. I'm using it in my compiler class right now. It does all the dirty work of, building all the automata to handle scanning and parsing your code. And you can define compilers really easily. It's really cool. And that is why Facebook used OCaml to create Flow, which is their new static type checker for JavaScript. Really slick. JavaScript, a lot of runtime errors due to passing in a string where it expected an integer. And you don't like runtime errors. And so this, with Flow, you can do a static analysis. You can do type annotations in your JavaScript, or it can also infer the type. For example, right here, we just have a little decorator that says flow. And it says, hey, I recognize the fact that this is going to return an integer. And then in our code, we're calling hello world, and it's saying, hey, dude, flow. This type is incompatible. So it analyzes your code and can, help prevent you from shooting yourself in the foot. If you want to install flow, just download the OCaml package manager, OPAM, install flow type. Simple as that. Jane Street is also the second big company that uses OCaml. They're the largest industrial user of OCaml. They're a quantitative trading firm here in New York City. They build core, and this is their wonderful blog. The link is in the slides, but you are watching this on YouTube, so you can't click on that link. But just Google it if you want to read more about OCaml. And then the last thing I wanted to say is, if you want to learn OCaml, seriously, all you need is real-world OCaml. I mean, you'll need more later, and you'll need Stack Overflow, and maybe OCaml.org is a good resource too. But real-world OCaml is gigantic, and it's got everything in there. And it uses core, and it does everything. Just read that book, and you'll be an OCaml god. That's all you really need. You probably need some love too. And last, I just want to thank Major League Hacking. You guys are sweet. And thank you, Shy, especially, for working hard. Thanks to everyone else at MLH who's working hard, whose name I don't know. And last, I just want to plug HackNY. I love HackNY. So if you're out there, apply for the HackNY Fellowship. I did it last summer, and it's just the greatest experience you could ever have. As long as you like New York City, you're going to love it. So I think that's it.